Back. Today we're going to consider maps in detail, but just by way of review. A relation, R, is a subset of A cross B if it's a relation between those sets. It's a map or a function if, we're going to get used to reading this notation, for all little a in the set A, there exists a B in the set B such that the pair AB is in relation. Or in other words, every element in A gets connected somewhere in B. Right? That's the idea of a function. We have to connect everybody somewhere. But also, this is the property called well-defined if AB is in the relation, that is if A gets connected to B, and AC is in the relation, then B must equal C. Otherwise, I'm sending A two different places, and that's illegal for a map, not for a relation. When we have this setup, we call A the domain of the function. And what do we call B?
Codomain.
The codomain. It's not the range. We'll get there. The range is a set of all things that get sent somewhere. The codomain is where I choose my destinations from. I don't necessarily reach all of them. Okay, so that's the relation idea that underlies this, which means it's all about sets. Right? Functions can be described completely in terms of sets. But layered on top of this, what I want to do now is introduce the usual function notation to see how it's connected. Let's scrub this. In the more standard notation, we say f is a function or a map from A to B. Precisely, under that same definition, that it connects every element of A to an element of B. That is the same definition, just different notation. Where if the pair AB is in the underlying relationship, then we write so these two things have the same meaning. The pair AB is connected in a relationship means that when I apply F to A, I get B. So this means that we can describe functions in various ways. One is we can list the pairs. That gets real tedious if the sets are big, right? But for very small sets, I could list the pairs. And you've seen this way back a long time ago in functions somewhere. I just list the ordered pairs. We'll give some examples of this in a bit. Another way that's equivalent to this is with a bipartite graph. Which is just fancy language, and I want to put that one up as an example. You've actually done this, you just didn't know the name of the thing. So if I have my set A having the members little a, little b, little c, and little d, I'll make them nodes in a graph. If I have my codomain having the nodes 1, 2, 3, and 4, how do I make my function? I simply connect each element of A to exactly one element of B. So I might do something like this. A goes to 2, B goes to 1, C goes to 3, and D goes to 2. So that's a nice visual way of saying that the ordered pair, A2 is in the list, the pair B1 is in the list, the pair C3 is in the list, and the pair D2 is in the list. Now, have I broken any rules in this particular example? Is it really a function? Did I send every element of A somewhere? And did I ever send one element of A to more than one place? It's a function, it's a map. It doesn't happen to reach everybody here, and it happens to send A and C, A and D to the same place, but that's okay, it's not illegal. As we'll see with a major example, the usual way we do this, because this is impractical except for trivial examples, is we give a rule or an equation. This is a common way of specifying a map or a function. And we've played with these for years, right, from high school on. And I want to now go there and give a couple of examples. So we could define f of x, where f goes from the reals to the reals, as f of x equals x squared minus 5. That's a rule that sends one to the other. Or maybe on the integers, so there's two examples. In this case, the domain and codomain would be the same, right? They're just all the real numbers. Here, the domain and codomain are all the integers, and we have a rule that sends one to the other. So this is the more common way of describing functions, although we'll see others as we go forward. Okay, so functions are interesting. They let us define rules for connecting the pairs, even if they're infinite. Now, a couple of things more definitions we want to clarify is what is the range, what's the image, and what is one-to-one and onto. These are the four big properties that we want to concern ourselves with. So let F be a map from the set A to the set B. We say the range of the function f can be written this way. The set of all elements in B that we actually get to. Well, how would we describe that in terms of the underlying relation? Such that there exists some A in A, that what, in terms of the relation? So that's the relation way of looking at it, right? The range is the set of all the B's I actually get to. That is the set of all the B's that appear as the second element in ordered pairs. They're the ones that get connected to. But that's the same as saying this. It's the set of all B in the codomain such that there exists an A in the domain with f of A equal B. In other words, it's all the B's I get to. So for the function side note here, f of x equals x squared on the reals. What are all the real numbers I get to through that map? Or easier to say, which are the ones I can never reach with this map? Which are the negative values I can never reach, right? So the range of f in this case is x greater than or equal to 0. Right? You know, all positive real numbers and 0. But I can never get a negative number out of that map, so no negative value is in the range of the function, because I can never get there. Now, another definition associated with range, or this, you have it. And these definitions are all given in our textbook and our section on maps, but it's helpful to talk about them. Suppose I pick some subset of my domain, and I want to figure out, in effect, what's the range of that subset. We say that the image of S under the map F it's all the B that I reach with this map. So it's the same thing, except I'm restricting my view to some subset S of the domain. It's all the elements in B that I can get to using only elements in S, the subset, as my source. And this has a nice shorthand notation. We write it simply as F of S. So when I apply a function to a set, that's what I mean. It's the set of all the answers I get. Think of this as a set of all results. Of applying the function to. And so another way to write the range then of this function is simply with this notation. It's the image of the domain as I apply the function, the image of everything. So that's not too hard. Let's do a trivial example on the side to keep this clear. Now let's do it this way. So here's my real function, x squared, from the reals to the reals. I'm going to choose as my subset S, z. So what would the image of z look like? Right, the image here is a smooth curve, right? It's that whole, all those points that make up the parabola. But the image of z under this map would simply look like a discrete set. That's it, right? You never get negatives out. If I put 0 in, I get 0. I put 1 in, I get 1. I put 2 in, I get 4. Put 3 in, I get 9, 25, etc., right? So the image of the integers as a subset of the reals under this map is just all the squares, right? A set of squares. Because these are all the ones I get to by squaring every integer. Okay, so all this I hope you've seen before somewhere. You should have seen this in discrete. I'm now going to introduce maybe a little bit more formally here, but it's the same ideas. The next thing I'm going to introduce is probably new. It's the idea of a pre-image, and it's really important in algebra. The pre-image of a value is the set of everything that gets sent there. So this is the set of all, excuse me. It's the set of all A in A such that f of A equals B. So I pre-image, I look at an element here and I see everything that's sent it there. How do I know, first real question of the day, how do I know the pre-image is never empty? Well, it can be, right? If no one ever gets sent to B, then its pre-image is the empty set. I don't have to touch every element in here. So this can be empty if B is not in the range. It's often one element, but it could be several. Consider the example. Again, f of x equals x squared. What is f inverse of 9? Pre-image of 9. Anything else? Negative 3. Yeah, there we go. Right? There's two different values that get sent to 9 by the squaring operator in the reals. If I have a cubic equation, a general cubic, the pre-image of 0 would be these 3 points where it crosses, right? So there can be lots of things that get sent to the same place. The pre-image of 1 might be those 3 points. Right? So pre-image is kind of a generalized inverse. It lets me pick one element in the codomain and figure out all the things that get sent there. So this would be f inverse of 1, and this would be f inverse of 0 under the cube, appropriate cube map that does that. And so this is called a pre-image of an element. As we dig deeper, we'll see these are important, and even at this level they're important, right? They're all the answers, we might say, to solving a problem f of x equals 1 or f of x equals 0. Okay, I'm going to extend this now to the pre-image of a set, and it's the same idea. Suppose R is a subset of B, then the pre-image of R is the set of all A in A, the set of all elements in real, such that f of A, now what do you think? It's not equal to B, because we have a whole bunch of B's. What do you think would be the generalization of this? It's not all the A's that go to one B, it's all the A's that get sent to any element of the set. So this would be the pre-image of the entire set. Okay. Let's pause here for a minute. Kill the same button to stop.